morning, good afternoon, and good evening to everyone who joins us from around the world. We're so glad you're here. This is Andrew Renee. Welcome to the Stack series.
Yes, thank you so much for tuning in. It's really wonderful to be here.
Today, we are exploring effective field theories. And I just have to be completely honest right up front. When I first looked through the source materials for this, I had a genuine moment of panic.
Oh, really?
A
Moment of panic.
Yeah. I mean, usually when we sit down to discuss physics, we're talking about the big, glamorous stuff, the theory of everything, string theory, the multiverse, the search for that one single, beautiful, elegant equation that you can print on a T-shirt. The one that explains absolutely everything from the Big Bang all the way down to why my toast always manages to land butter side down.
Romantic dream of physics.
Exactly. The hunt for the ultimate fundamental truth. The bedrock of reality. But today, we are talking about something that sounds, well, the name itself almost sounds like a compromise. Effective field theory. It sounds like, the good enough field theory. Like we couldn't figure out the actual real answer, so we just came up with an effective one.
That is a very, very common misconception.
But as I started actually reading the sources, the papers by Donahue, the philosophical breakdowns by Bain and King, I realized my initial reaction was completely backwards.
It really is. We have this bias, I think, to believe that the most powerful tool in all of science is the microscope.
Yeah.
The ability to just zoom in deeper and deeper and deeper.
Right.
But what if I told you that arguably the most powerful tool we have in theoretical physics is actually the ability to systematically ignore almost everything?
See, that is the hook right there, the art of ignoring things. Because if we really unpack this, it makes perfect practical sense. I mean, let's say I want to design a submarine. I need to know about fluid dynamics, right?
Correct. You need the Navier-Stokes equations.
I need to know how water flows around a steel hull. I need to understand pressure, viscosity, maybe some turbulence.
Exactly. The bulk properties of the medium.
Okay, but do I need to know that water is made of H2O molecules?
Well, ideally, yes. Knowing the chemical composition is helpful for understanding why the density is what it is.
Sure. But do I need to know about the quarks? Like the quarks vibrating inside the protons, inside the nucleus of the oxygen atom of that water molecule to build my submarine?
Absolutely not. In fact, think about that scenario for a second. If you actually tried to calculate the drag coefficient on a submarine hull using the equations for quarks and gluons,
That'd be fire.
you would never even finish the calculation. The universe would experience heat death before your supercomputer solved the equation for the first millisecond of the submarine moving an inch.
Wow.
It's computationally impossible. But even more importantly than that, it is physically irrelevant.
And that is the core concept we are going to unpack today. This is what the source material calls decoupling, right?
Precisely. The physics of the very small decouples from the physics of the large. They basically stop talking to each other in a way that matters. And this brings us to what I think is the most helpful metaphor for this entire discussion, which is resolution.
I love this analogy from the text. It's like looking at a digital photograph.
Right. Imagine you are standing across the room, looking at a massive, high-resolution photograph of a forest. From that distance, you see trees, you see shadows, maybe a little stream cutting through the middle. The image looks completely smooth and continuous.
And the laws describing that picture are about shapes and colors and lighting.
Exactly. That is your low-energy or long-distance view of the world. But if you walk right up to the photograph and you zoom in, really zoom in, eventually that smooth, continuous picture breaks down entirely.
You start seeing the square pixels, the little red, green, and blue dots.
Right. The laws of the trees and the shadows completely disappear. Suddenly, you are only dealing with the laws of pixel grids and RGB values. Now, here is the real kicker of this whole concept. To describe the forest to someone, you do not need to know about the pixels.
The pixels are irrelevant to the forest.
Exactly. The pixel theory is the fundamental theory of the digital image, sure. But the image of the forest is the effective theory. And it works perfectly fine at the scale you are actually looking at.
So physics, as it turns out, is basically just a giant stack of these pictures at different zoom levels.
That is exactly our roadmap for today. We are going to look at the architecture of the universe through these specific layers. We're going to dive into how physicists actually build these theories. We'll explore how this specific approach has revolutionized our understanding of gravity.
Which blew my mind, by the way.
It's incredible stuff. And finally, we'll talk about why this fundamentally changes the philosophical definition of what truth even means in science.
Okay, let's jump right into the foundations. Part 1, what do we actually think we know?
Let's stick with that idea of decoupling we just mentioned. Because the fundamental premise of an effective field theory, or an EFT, is that physical processes happening at a specific energy scale, which we usually just call E, are largely completely insensitive to the details of physics at a much higher energy scale.
And that higher energy scale is called Lambda in the literature, right?
Yes, Lambda. You can think of Lambda as the cutoff scale.
It's the here be dragons line on the map.
Or the here be pixels line. As long as you stay well below that cutoff scale, you simply don't need the high energy details. A really classic example that the sources mention is Rayleigh scattering.
Okay.
Now tell me, why is the sky blue?
Because, well, the simple high school answer is that sunlight scatters off the atmosphere.
Right. Light from the sun hits the atoms in the air. Blue light has a shorter wavelength, so it scatters more easily than red light, and therefore the sky looks blue to our eyes. Now, to calculate this mathematically, Lord Rayleigh used an effective theory. He looked at light interacting with small, neutral spheres. He basically just treated the nitrogen and oxygen atoms as little solid balls.
Okay, but he didn't know about quantum mechanics when he did that.
No, not in the modern sense at all. And he certainly didn't have the full microscopic picture of an atom. But here is the critical question. To explain the blue sky, do you actually need to use the Schrödinger equation to map out the complex electron orbitals of a nitrogen atom?
Probably not. That sounds like a lot of unnecessary math just to explain a color.
Right. Do you need to know about the nucleus buried deep inside that atom?
Oh.
Do you need to know about the quarks and gluons inside the protons inside that nucleus?
Definitely not.
Exactly.
Yeah.
All of those high-energy details, the intense internal structure of the atom, are completely irrelevant at the relatively low energy scale of visible light. The light ray just sees a tiny obstacle and bounces off. It doesn't care what is inside the obstacle. The heavy, high-energy physics has successfully decoupled from the low-energy physics.
It really is amazing when you step back and think about it. If humanity had to understand the ultimate, final theory of everything just to figure out why the sky is blue, we would literally still be in the Dark Ages.
We would be paralyzed.
We wouldn't be able to understand anything until we understood absolutely everything.
And that is why science relies so heavily on this decoupling principle.
Yeah.
The sources also bring up the hydrogen atom as another great example. We have the standard model of particle physics today. It includes quarks, gluons, the weak nuclear force, the Higgs boson. It is by far the most complete, rigorous theory we have ever constructed. But if you want to calculate the basic energy levels of a simple hydrogen atom, the kind of standard calculations you do in undergraduate chemistry using the full standard model is, as one of the papers notes, massive overkill.
It's like using a chainsaw to cut a piece of sandwich bread.
It's incredibly cumbersome and entirely unnecessary. Instead, we use an effective description where we just treat the proton in the center as a single heavy point particle. We completely ignore its internal quark structure. And guess what?
It works.
It works beautifully. It gives you the correct answer to a staggering degree of precision.
So how do we actually build one of these things? If a theoretical physicist sits down today to construct an EFT, what is in their toolkit?
The very first step is identifying your degrees of freedom.
Meaning the players on the field.
Exactly. At low energy, your players are protons, neutrons, and electrons. At high energy, your players are quarks and gluons. Once you pick the players that are actually relevant to your specific energy scale, you have to figure out what to do with the players you are ignoring.
And this brings up a phrase I saw over and over again in the literature. Integrating out.
Yes.
Integrating out the heavy fields. It sounds so incredibly bureaucratic. Like, I'm sorry, Bob, but management has decided to integrate you out of the department.
It is a bit like that. Imagine you have these super heavy particles, the ones that require massive amounts of energy to even create in a collider, like the W boson or the top quark. At low everyday energies, those heavy particles can't really move around or do much of anything. They just sort of vibrate in place. Their existence is fleeting.
They're just background noise. They pop in and out of existence so fast that we don't even see them as distinct individuals.
Exactly. So mathematically, integrating out means we take those complicated, fast-moving, high-energy vibrations and we blur them out into the background. We replace their complicated dynamic equations with a simple constant number. We effectively shrink their influence down to a single point.
And that leads us directly into the Lagrangian expansion. Now, I promised everyone listening that we wouldn't turn this into an advanced calculus class.
We won't, I promise.
But we do have to explain a concept called power counting. Because based on the source texts, power counting seems to be the absolute magic sauce of effective field theory.
It really is the magic sauce. And please don't be intimidated by the name. Power counting is actually a very intuitive, practical way of organizing information. If you remember taking calculus, think of it a bit like a Taylor series.
I remember the term vaguely. It's about approximations, right? Like representing a complex curve as a series of straight lines.
Close enough. It's a mathematical way of representing a very complicated function as a sum of much simpler terms. The first term in the series is the most important one. The second term is a small correction. The third term is an even tinier correction, and so on.
Okay, I think the absolute best way to explain this to the audience is the table measuring analogy we were talking about before we started recording, because that is what finally made it click for me.
Yes, let's use the table. Suppose I ask you to measure the length of the wooden table sitting right here in the studio between us.
Okay, so I just eyeball it and I say, it's about 2 meters long.
Good. That is your first order approximation. In the language of EFT, that is your renormalizable core. It describes the gross dominant structure of the physics, that 2 meters gets you 90% of the way to the truth.
Right, but then you hand me a tape measure.
Right. Now I want you to measure it more carefully.
So I look closer and I see it's not exactly 2 meters. It's actually 2 meters and 5 centimeters.
Okay, so you have just added a correction term, the centimeters. In physics, this is what we would call a higher dimension operator. It adds detail, it refines the picture, but its overall contribution is much smaller than that first dominant term.
And then let's say I get incredibly obsessive about this table. I pull out a set of high-precision calipers.
Now you're measuring the millimeters. So the full length is 2 meters, 5 centimeters, and 3 millimeters.
The 3 millimeters is the next correction term in the series. And conceptually, I could just keep going forever, right? I could get an electron microscope and start measuring the individual microns of the wood grain. I could measure the microscopic atomic bumps on the varnish.
You absolutely could. But here is the central defining question of effective field theory. When do you stop?
Well, practically speaking, I stop when I just don't care anymore.
Exactly. If your only goal is to figure out if this table will fit through the door of the studio, do you care about the microns?
No. The doorway is 1 meter wide. I only need to know if the table is 2 meters or 1 meter. The millimeters and microns are completely irrelevant to moving the table.
In physics, this stopping point, the point where you stop caring, is determined by the energy scale you are operating at. We call it power counting. We organize our mathematical equations so that the first term is the biggest. The second term is divided by a very large number, which is our cutoff scale, lambda.
Right, lambda, the here be dragons line.
So that second term is basically multiplied by a fraction your energy divided by lambda. If your operating energy is very small and the cutoff lambda is huge, that fraction is a tiny, tiny decimal. It's like measuring our studio table in kilometers. The number is something like 0.002. It essentially vanishes.
And the next term in the series is that fraction squared, right?
Exactly. So the next term is energy over lambda squared. Then the next is cubed. So these terms get microscopically tiny, incredibly fast. The higher you go up in the series, the less it matters. And this mathematical fact gives physicists the permission to just chop off the end of the equation.
Which is called truncating.
Truncating the series, yes. We write down the first few terms and we just say, eh. The rest of this is far too small to matter at our current energy scale.
See, when you phrase it like that, it feels a little bit like cheating. It feels like you're just purposely ignoring the really hard parts of the math.
But it's not ignoring them out of laziness. It is mathematically acknowledging that those higher terms are physically suppressed by the scale of the universe. Unless
you start looking closer.
Right. If you zoom in, meaning if you jack up the energy level in a particle collider, suddenly your energy gets closer to lambda. That fraction of energy over lambda isn't a tiny number anymore. If you look at our table with that electron microscope, suddenly the micron term is huge and incredibly relevant.
And that is exactly when the effective theory breaks.
That's when the effective theory fails, and you are forced to find a new, deeper theory to explain what you're seeing at that higher resolution.
This whole framework really helps explain the difference between the top-down and bottom-up approaches, which I saw heavily debated in the literature.
Yes, that is a crucial distinction to make.
So, if I understand correctly, top-down is when we already know the big, complicated, fundamental truth, and we actively choose to simplify it, like taking a massive raw image file and downscaling it so it loads faster on a website. We know exactly what the pixels are, but we choose to blur them together for efficiency.
A perfect historical example of the top-down approach is the Fermi theory of beta decay. This takes us all the way back to the 1930s. Enrico Fermi wanted to explain how a neutron decays into a proton, an electron, and a neutrino.
Which is the weak nuclear force at work. This is literally the physics that powers the sun.
It is. Now, here is the genuinely amazing part about Fermi's work. In the 1930s, Fermi did not know about the existence of the W boson. Today, we know the W boson is the heavy particle that actually mediates this weak force. It's the messenger particle that carries the information for the decay to happen. But the W boson is incredibly heavy. It has a mass of about 80 giga-electron volts, or GeA.
And the actual decay of the neutron happens at what energy level?
Very, very low energy, about 10 mega-electron volts.
Okay, so the W boson is insanely massive compared to the energy of the actual event. It's like a heavy bowling ball trying to influence a slow-moving game of glass marbles.
The mass difference is huge.
Oh.
So because Fermi didn't know about this massive messenger particle, he described the interaction as just 4 particles meeting at a single exact point in space. Just pop, the interaction happens instantly. He successfully integrated out the W boson without even knowing it existed.
He treated the W boson as a single pixel.
Effectively, yes. He replaced the travel time and complex dynamics of the W boson with a simple contact interaction. And because the energy of the neutron decay was so incredibly low compared to the mass of that hidden W boson, his theory was shockingly accurate. It was a flawless, effective field theory for that energy scale.
That's the top-down approach, or at least looking back from today, it's top-down because we eventually found the W boson. We know the full high-res story now. But what about the bottom-up approach? How does that work?
Bottom-up is exactly what we are attempting to do right now at the Large Hadron Collider, the LHC, in Switzerland. We strongly suspect there is new physics out there waiting to be discovered. Dark matter, supersymmetry, something much heavier than the particles we currently know. But we don't know what it is yet. We do not have the full theory.
We don't have the high-resolution photo. All we have is the blurry, low-res picture of the standard model.
Exactly. So scientists build a framework, specifically the Standard Model Effective Field Theory, which we usually call SMEFT, to mathematically constrain what that high-res photo could possibly look like. We look at the collider data to try and find those tiny millimeter-level correction terms we talked about earlier. If we find those tiny deviations, they point like a compass toward the cutoff scale, toward the hidden new physics.
It's essentially detective work. You're searching for the subtle fingerprints of heavy, undiscovered particles hiding within the low-energy data. You haven't caught the killer yet, but you can clearly see the depth of their footprint in the mud.
Precisely. And analyzing the exact shape and depth of that footprint can tell you a lot about the mass and nature of the hidden particle.
Okay, we have to talk about the elephant in the room now. The concept that apparently made mid-century physics students wake up in a cold sweat. Renormalization.
Ah, yes, the R word.
Historically, physicists absolutely hated this, right? The sources talk about how people in the 1940s and 50s were doing calculations in early quantum field theory, and the math kept spitting out infinity as the answer. And normally, if you're doing a math problem and the answer comes out as infinity, it means you messed up.
It was considered a massive crisis in the field, a genuine intellectual roadblock. You would sit down to mathematically calculate the mass of an electron, and the equation would blow up and say the mass is infinite. But we go into the lab, we measure a real electron, and it obviously has a very specific, finite, tiny mass.
Right. So to fix this, they invented the math of renormalization, which at the time some very famous people called a shell game, or just sweeping dirt under the rug. Basically, you strategically subtract infinity from infinity in order to leave behind a nice, neat, finite number.
Even Richard Feynman, who helped pioneer it, was highly suspicious of it initially. He famously called it hocus pocus. But the advent of effective field theory completely reframes this entire problem. It stops being a dirty mathematical trick and becomes a profound physical insight.
Please explain that, because how does an EFT framework make getting an answer of infinity somehow okay?
Because EFT tells us that those infinities are just a mathematical artifact of our own ignorance. They only appear because we are trying to run our mathematical integrals all the way up to infinite energy, basically assuming our current theory holds true forever. But we already established that our theory does not hold forever. It hits a cutoff scale, Lambda.
Oh, so the infinity isn't real. The infinity is actually just the math trying to tell us about a really big number related to that cutoff point.
Right. And here's the real conceptual breakthrough. We can never actually measure a bare, isolated electron in a lab. We can't peel away the electromagnetic field and see the naked particle underneath. An electron is always surrounded by a buzzing cloud of virtual particles. We always measure the electron plus its cloud.
And this brings us to the Wile E. Coyote analogy from the source text. I literally laughed out loud when I saw a classic cartoon coyote being used to explain quantum field theory. But it is such a vivid, helpful image.
It's a brilliant pedagogical tool for this exact concept. Imagine Wile E. Coyote running off a cliff and falling. If you want to calculate how long it takes him to hit the ground, what variables do you actually need?
I need the force of gravity, and I need his mass.
Right. Now, do you need to know the complex atomic structure of the coyote's bones?
No.
Do you need to know exactly how many individual fleas are living in his fur, or calculate the microaerodynamics of every single hair on his body?
Definitely not.
Those microscopic high-energy details are renormalized into his total mass. When you put Wile E. Coyote on a scale, you're weighing the atoms, the bones, the fur, the fleas, everything all together as one package.
Yeah.
You measure one single number, his total mass.
So renormalization is really just the universe saying, look, we don't know the intricate details of the quantum fleas, but we measured the total weight of the package in the lab, so let's just use that number and move on.
Exactly. The unknown high-energy details, the fleas and the atoms, are quietly absorbed into the low-energy constants that we measure. We measure those constants experimentally, we plug them into the equations, and suddenly all the infinities just naturally disappear.
When you explain it like that, it sounds incredibly sensible. It's not a mathematical hack, it's just an honest admission that we only ever interact with the package deal, not the raw fundamental components.
It is the ultimate expression of scientific pragmatism. It mathematically proves that we do not need to understand the physics of the Planck scale just to do basic chemistry. The microscopic fleas of the universe are safely absorbed into the constants we use every single day.
Okay, so that perfectly covers the foundation. We systematically ignore the small stuff, we absorb the unknowable details into measurable constants, and we build our understanding of reality in layers. But as with all things in science, it's not all smooth sailing. There are some intense debates happening right now in this specific field.
Oh, massive debates. The physics community is never completely settled.
Let's transition into part 2, the active debates, starting with the hierarchy problem. Now, whenever I hear the word hierarchy, I think of corporate management structures. But in this context, I gather it's primarily about the Higgs boson.
It is. And it is arguably the biggest, most persistent headache in modern theoretical particle physics. We finally discovered the Higgs boson at the LHC in 2012, and we measured its mass. It weighs about 125 GeV.
Which means nothing to me contextually. Is that considered heavy or light?
In the grand cosmic scheme of the universe, it is incredibly suspiciously light. According to the standard tried-and-true principles of EFT that we just discussed, the mass of the Higgs boson should be highly sensitive to the highest energy scales in the universe, specifically the Planck scale.
And the Planck scale is the absolute limit, right? That's where gravity becomes quantum and our understanding of space and time basically breaks down. That's way, way up there.
It's massively high. The Planck scale is around 10 to the 19th power GeV. Now, because of how quantum fields interact, the quantum corrections, those high-energy fleas we talked about, should theoretically be dragging the mass of the Higgs boson way up toward that massive Planck scale. The Higgs should be enormously heavy.
So it's kind of like, imagine we're out hiking, and we find a small pebble on the ground, and we pick it up, and it weighs exactly as much as a normal pebble. But the fundamental laws of quantum geology explicitly state that because there are massive mountains nearby, the gravitational influence of those mountains should somehow make this pebble weigh as much as Mount Everest.
That is a fantastic analogy, yes.
Yeah.
And because the pebble in our hands does not weigh as much as Everest, because the Higgs is only 125 GeV, we're forced to ask a very uncomfortable question. Is nature deeply fine-tuned? Did the universe somehow dial in two gigantic opposing numbers, one positive and one negative, that perfectly cancel each other out to 30 decimal places, just to leave behind this tiny, delicate remainder of a mass?
And physicists absolutely hate the idea of fine-tuning, don't they? It feels like a massive cheat. It feels like the invisible designer of the universe just manually adjusted the dials behind the scenes to make it work.
They despise fine-tuning, because it strongly suggests that we are missing something fundamental about how reality operates. This is what the sources refer to as the crisis of naturalness. Standard EFT logic says this perfect cancellation shouldn't happen naturally. The core decoupling principle suggests that the extreme high-energy stuff should absolutely pollute the low-energy stuff in this specific case, but it doesn't.
And this baffling problem has led to some pretty wild speculative ideas. The texts spent a lot of time on something called UV-IR mixing.
Yes. So remember how we spent the first 20 minutes establishing that the high energy, the ultraviolet or UV scale, and the low energy, the infrared or IR scale strictly decouple?
Yeah.
That they absolutely do not talk to each other.
Right. The submarine does not care about the quarks.
Well, the severity of the hierarchy problem has led some physicists to suggest that maybe, just maybe, they do talk to each other. UV-IR mixing is the radical idea that perhaps, under certain extreme conditions, the physics of the very small and the physics of the very big are somehow deeply correlated.
So the pixels actually do determine the overall picture.
Or the big picture fundamentally determines the behavior of the pixels. It completely breaks the foundational assumption of effective field theory. There are certain exotic theoretical models, like non-commutative field theory, where this kind of mixing actually happens naturally in the math. It was a massive departure from standard physics.
I mean, if that's true, it's like finding out that the drag coefficient of the submarine actually does depend on the specific vibration of the quarks inside the water molecules. That would be an absolute mess.
It would be a computational nightmare for us. But it might actually be the only mathematical way to solve the puzzle of the Higgs mass. It suggests that the neat, isolated layers of the physical onion aren't quite as separate as we confidently thought they were.
There's another debate in the materials that really caught my eye, and it's about whether renormalizability is actually a strict requirement for a theory. Because earlier, I thought you just explained that EFTs successfully fixed the whole fear of infinities.
It did fix it, but it fixed it by completely changing the rules of the game. See, the old school view, pretty much everything before the 1970s, dictated that a physical theory is only considered good or valid if it is fully renormalizable at absolutely all energy scales. It has to be able to mathematically handle infinities perfectly all the way up to infinite energy.
So it has to be a perfect theory. It has to work flawlessly from our perspective all the way up to the perspective of God.
Essentially, yes. But the modern EFT view came along and said, who cares? Non-renormalizable theories are perfectly fine. We can still use them. They just have a built-in expiration date, which is the cutoff scale. They are highly effective and predictive up to a very certain point, and then they completely fail. But as long as you stay within their valid range, they're incredibly useful.
So this shift in perspective basically rehabilitated a bunch of older theories that were previously thrown out as being fundamentally broken.
Completely. It turned so-called bad theories into limited theories. And honestly, since we strongly suspect that every single theory we currently possess, including the mighty standard model, breaks down eventually at some high energy scale, accepting limited theories is a much healthier, more humble scientific perspective.
But logically, doesn't that just lead us straight into an infinite regress? Because this transitions perfectly into the philosophical debate outlined in the sources, the argument between the top-down view and emergence.
This is where the physics bleeds directly into deep philosophy. There's an ongoing debate between philosophers of science, like Cow and Schwaber, and the strict reductionists. The fundamental question they're arguing over is this: is there actually a bottom to physics?
A basement level where the rules are finally set in stone, the ultimate bedrock of reality.
Right. Or is reality just an infinite tower of effective theories? Think about it. Maybe you peel back the particles of the standard model and you finally find vibrating strings, but then you peel back the strings and you find, I don't know, preons.
Yeah.
And you peel back the preons and you find something else entirely, just layers ad infinitum.
And the completely opposite side of that coin is the concept of emergence. Does the low-energy physics emerge with totally brand new laws that are functionally independent of the high-energy stuff beneath it?
The source material provides a beautiful, very concrete example of this. Superfluid helium-4. This is a fascinating macroscopic substance that, when cooled near absolute zero, flows completely without friction.
Oh, is it the liquid you see in lab videos that seemingly defies gravity and just slowly climbs up and out of the glass beaker?
Yes, exactly. That's the stuff. Now, if a physicist studies the sound waves moving through this superfluid at low energies, those waves obey a very specific, rigorous set of mathematical equations. In fact, if you look at the math, it looks exactly like a relativistic field theory. The sound waves obey equations that perfectly mimic high-energy particle physics, but with a strict speed limit, the speed of sound, rather than the speed of light.
Okay, but we know for a fact that the underlying helium atoms making up the fluid are not moving relativistically at all. They're just standard, slow-moving, freezing cold atoms.
Exactly. The apparent relativity emerges organically from the collective system. It absolutely was not present in the base ingredients. If you were a tiny conscious observer living entirely inside that superfluid, you would measure your world and swear on your life that the fundamental laws of the universe were relativistic. You would calculate the speed of sound and declare it to be the ultimate cosmic speed limit.
And from their perspective, within their effective scale, they would be 100% right.
They would be completely right about their specific effective world, but they would be completely wrong about the fundamental microscopic nature of the helium atoms they are made of. This directly challenges strict reductionism. You simply cannot derive the complex behavior of a swirling superfluid just by staring intently at the properties of a single, isolated helium atom. As the physicist Philip Anderson famously wrote in his paper, more is different.
That is genuinely mind-bending to think about, because it implies that scientific truth heavily depends on where you are currently standing on the ladder of energy scales.
It implies that completely new, profound physical laws can naturally appear at larger scales that are totally invisible and completely unpredictable if you only look at the microscopic scales below them.
Before we move on to the frontiers section, I have to bring up a term I saw in the string theory section, the swampland. Now, the swampland sounds like a dangerous location in a high fantasy novel, the quest through the swampland, but it's actually a formal physics concept.
Yes, it is. The swampland is the collective term for all the theoretical effective theories that look mathematically consistent on paper but cannot actually exist in reality because they cannot be derived from a valid, consistent, high-energy parent theory like string theory.
So they're essentially imposter theories.
They are absolute imposters. In this framework, string theory acts kind of like a cosmic bouncer at a club. It places very strict constraints on what is allowed to exist in the low-energy world. Just because you can write down a mathematical equation that looks like a good EFT does not mean that equation is permitted to exist in a universe ultimately governed by quantum gravity.
So if your proposed EFT violates the bouncer's constraint,
If it's kicked out of the club, it is relegated to the swampland rather than the landscape of possible valid universes.
it's like an AI generating a low-res picture of a square circle. Sure, it's a picture and it exists on your screen, but it fundamentally represents a geometric impossibility that could never be constructed in physical reality.
Exactly. The swampland concept is incredibly useful because it helps theoretical physicists filter out models that are mathematically plausible in isolation, but physically impossible when connected to the deeper laws of quantum gravity.
All right, let's pivot to part 3, the absolute frontiers of this science. Because one of the biggest, most pervasive myths in pop science communication, and I am personally guilty of repeating this very myth in past discussions, is the idea that quantum mechanics and general relativity are fundamentally incompatible.
Oh, I hear this repeated every single day. Gravity violently clashes with quantum mechanics. The math breaks down entirely. We desperately need a brand new theory of quantum gravity. It is the standard, reliable, dramatic tension of almost every physics documentary produced in the last 30 years.
But according to the deep dive into the sources, specifically the groundbreaking work by physicist John Donahue, this whole dramatic narrative is, well, it's basically wrong.
It is largely a myth. Or, to be more precise, it is a severely outdated view of how physics actually works. Donahue and several others have rigorously shown that Einstein's general relativity works perfectly fine right now as an effective field theory.
Wait, let me stop you there. Are you saying we already have a working theory of quantum gravity?
We have a working theory of effective quantum gravity.
Mm-hmm.
If you simply treat general relativity as a low-energy EFT, you can actually quantize it. You can do the complex mathematical loops. You can successfully calculate quantum corrections to gravity.
But I thought the whole problem was that gravity is non-renormalizable. I thought if you tried to quantize it, the equations instantly blew up with unmanageable infinities.
It is entirely non-renormalizable in the strict old-school sense we talked about earlier. But remember the new rules we just learned. That doesn't matter anymore. As long as you stay at low energies and in the context of gravity, low energy means anything below the monstrous Planck scale. The effective theory of quantized gravity works beautifully.
So, if we're looking at the energy scales of our everyday solar system, or even the intense crush at the center of a star, we can happily mix gravity and quantum mechanics together without breaking the universe.
Yes, we just take the mathematically annoying, uncontrollable high-energy parts of the equation and we lump them together into unknown coefficients, just like we did with the fleas on Wile E. Coyote. The high-energy ignorance is absorbed, but the low-energy quantum effects of gravity are completely calculable.
Okay, if they are calculable, can we actually measure these quantum effects of gravity in a lab?
Well, that is the unfortunate catch. Donahue successfully calculated the primary quantum correction to the classic Newtonian gravitational potential. You remember Newton's law, right? The potential is negative g times mass 1 times mass 2, all divided by the distance, r.
Classic high school physics, the apple falling from the tree.
Exactly. Donohue's quantum correction naturally adds a new tiny term to that equation. And that new term is directly proportional to Newton's constant g, multiplied by Planck's constant, divided by the distance squared.
Okay, g times Planck's constant, both of those numbers are incredibly small. That correction must be infinitesimally tiny.
It is mind-bogglingly small. It is far too small to ever measure with any current technology or, realistically, any future technology we could ever dream of building. We're talking about an impact of something like 10 to the negative 80 meters on the massive orbit of the Earth around the Sun.
So, playing devil's advocate here, if we can't ever measure it, does it actually matter that he calculated it?
It matters immensely to physicists because the math proves that the core concept works. It proves the fundamental mechanism isn't inherently broken. It demonstrates mathematically that gravity can and does play by quantum rules at low energies.
And here is where the reading got really interesting for me. The text explicitly notes that this specific quantum correction term is quote-unquote universal.
Yes.
Universal how? What does it actually mean for this tiny, unmeasurable mathematical wiggle to be universal?
It means that it absolutely does not matter what the ultimate final theory of everything turns out to be. It could be string theory, it could be loop quantum gravity, it could be something we haven't even invented yet. It doesn't matter. They all have to produce this exact same low-energy mathematical answer.
Because all of those grand theories eventually have to funnel down and accurately recreate the world of general relativity that we observe.
Exactly. This specific quantum correction term acts as a strict gatekeeper. Any new candidate for a grand theory of everything must accurately reproduce this tiny 1 over r squared wiggle in the math. If a theorist comes to me with a fancy new 11-dimensional theory of reality and it predicts a different wiggle, I know immediately that their theory is wrong.
That is an incredibly powerful tool. It tightly constrains the shape of the theory of everything before we even know what that theory is, but there must be limits. Does this effective theory of quantum gravity ever completely fail?
Yes, it fails exactly where all effective field theories fail, near the cutoff scale. For gravity, the cutoff scale manifests in places of infinite density, singularities, and black holes.
The text specifically mentioned a problem called integrated curvature.
Right. EFT usually relies on the assumption of local effects, small, isolated things happening here and there. But gravity is unique because it naturally accumulates over massive areas. If you are hovering near the event horizon of an immense black hole, the gravitational curvature effects build up and integrate over huge distances. This massive accumulation can potentially break the local expansion math that EFT heavily relies on.
It's like the individual pixels of space-time are getting stretched and distorted until the whole image tears apart.
And at the singularity itself, the infinitely dense center of the black hole, well, that is exactly where the microscopic pixels become the size of the entire image. The effective theory successfully predicts its own violent demise. At a singularity, we genuinely, desperately need a new fundamental theory. That is where string theory, or something equivalent, absolutely must take over.
But for literally everything else, orbiting planets, the spin of galaxies, gravitational waves rippling through space, apples falling from trees, the EFT framework handles it flawlessly.
Flawlessly.
Okay, let's look at the other major frontier the text outlines, the Large Hadron Collider. We briefly touched on this earlier with the bottom-up approach, but let's dive deeper into SEFT, the Standard Model Effective Field Theory.
This is the dominant modern strategy for experimental particle physics today, because for decades, the entire field was intensely focused on looking for specific, predicted new particles. It was very targeted. Let's turn on the collider and find the Stopes quark. Or let's tune the energies to specifically hunt for the Z-prime boson.
Right. It's like going on a very specific hunting trip. You are solely looking for bear tracks, and you ignore everything else.
Exactly. And the harsh reality is we haven't found them. The LHC has been running incredibly complex collisions for many years now, and we simply haven't found the big, shiny, heavy new particles that theories like supersymmetry aggressively predicted. Other than the monumental discovery of the Higgs boson, the new particle searches have largely come up empty. So out of necessity, the overall strategy has profoundly shifted.
Because they can't just keep hunting for a bear that might not be in the forest.
Right, so instead of hunting for a specific theoretical beast, physicists are now using SFT to meticulously scan for the subtle footprints of literally any beast.
That's the model-independent approach.
Yes. We use the massive mathematical framework of SES-MFT to officially parameterize our own ignorance. We sit down and write out every single possible mathematical interaction that could theoretically exist between the particles we know, and then we measure the tiny tuning dials on those interactions. We call those dials the Wilson coefficients.
Okay, so the Wilson coefficients are the dials on the dashboard of the standard model.
Exactly. Now, if the standard model is truly all there is to reality, and there is no hidden new physics, then mathematically, all those extra dials should be sitting dead at zero. But if we analyze billions of collisions and we see one of those dials naturally twitch, even just a microscopic fraction of a millimeter, it definitively tells us that something heavy and unknown is pulling on the system from the shadows.
It's like staring at the dark shadow cast by a distant mountain. You can't actually see the mountain itself because of the fog, but just by studying the length and shape of the shadow, you can accurately calculate how tall the mountain must be and roughly where it stands.
That is exactly what SES-MFT does. It is a systematic, rigorous way of exploring the dark borders of the unknown without having to guess exactly what you were looking for beforehand. Now, admittedly, it is far less romantic for the public than announcing we discovered the magical supersymmetry particle, but it is rigorously, brutally honest science. It forces the community to humbly listen to what the raw data is saying, rather than artificially imposing our elegant theoretical dreams onto nature.
And relentless honesty is exactly what true science is supposed to be about. Which naturally brings us to the final part of our discussion today, part 4. The massive implications of all this. Because this entire EFT framework, it doesn't just change the math, it fundamentally changes how we perceive reality itself.
It absolutely does.
Yeah.
The philosophical shockwaves of EFT touch on deep ethics, economic modeling, and the core philosophy of existence.
Let's start with a concept from the reading called philosophical realism, or effective realism, because I have to admit, this is the part that genuinely kept me up at night after reading it.
It's a very deep rabbit hole.
Because if a quark or a proton is ultimately just an effective degree of freedom, if it's just a mathematically convenient variable that only exists at our specific zoom level, are those particles actually real?
That is the ultimate million-dollar philosophical question. And the source texts present a compelling view called effective realism. This philosophical stance suggests that physical entities are absolutely real if they are demonstrably robust and consistently detectable at their specific energy scale.
Okay, so the heavy wooden table in front of us is real, even though physics tells me it is technically 99.9% empty space and a buzzing haze of abstract quantum fields.
Yes. Under effective realism, the table is a completely real, valid, effective object. The proton is a real effective object. The fact that the table might mathematically dissolve into abstract quantum fields at a microscopic level doesn't make the solid table fake or an illusion. It just makes its reality strictly scale-dependent.
I really like that. I genuinely find that comforting. It completely saves us from that depressing existential trap of thinking that everyday life is just an illusion. You know, that annoying argument of, oh, you didn't really stub your toe on the chair, Andrew, because toes in chairs aren't fundamental particles.
Exactly. That kind of extreme reductionism is logically absurd when you try to live your life. Your pain is real, your toe is real, and the chair is definitively real. They are profoundly real entities operating within the highly complex, effective theory of a human being walking through a living room.
There is also an interesting economic parallel mentioned here, the concept of scientific economy.
Oh, absolutely. Effective field theory is, at its core, a massive engine of efficiency. It explicitly stops human beings from wasting finite time and computational resources calculating irrelevant, invisible details.
It perfectly mirrors how we manage complex systems in human society, doesn't it? Like in macroeconomics, we build models based on broad market forces. We talk about inflation rates, supply chains, aggregate demand. We do not attempt to map out the individual firing neurons of every single day trader on the floor of the stock exchange.
Right. Modeling the neurons would be the ultimate microscopic fundamental theory of the stock market, but it would be completely useless for setting interest rates. The effective theory of supply and demand works perfectly at the scale of a national economy. Sociology models large groups, not individual atomic collisions. When you really think about it, every single branch of science is, in a very real way, simply an effective theory of the more detailed layer below it.
That's a profound way to look at it. Biology is essentially just an effective theory of chemistry. Chemistry is an effective theory of underlying physics.
And fundamental physics is just an effective theory of Well, we don't know what yet.
Which brings us perfectly to the final, somewhat controversial idea discussed in the texts, the anti-foundationalist view.
This is a highly provocative thought to end on, but it is gaining traction. For literally centuries, dating back to the ancient Greeks, the entire enterprise of physics has been aggressively obsessed with finding the foundation, finding the absolute bottom of the pyramid, the indivisible bedrock of reality.
Democritus and the atom.
Exactly.
Hmm.
But the runaway success of the EFT framework strongly suggests something radical. It suggests that maybe, just maybe, there is no bedrock at all.
It completely changes the defining metaphor of physics. Instead of desperately digging down to find the bottom of a pyramid, maybe the universe is just an infinite onion. Or an infinite tower stretching down forever. We just keep peeling away layers and finding new layers and peeling those forever.
And mathematically, logically, maybe that is perfectly okay. Maybe the ultimate goal of science shouldn't be to definitively find the elusive final theory of everything. Maybe the true goal is simply to build the absolute best, most accurate map possible for the specific territory we are currently standing on.
It's actually incredibly liberating when you frame it like that. It means we don't have to know absolutely everything about the universe, just to confidently know something about our lives.
Precisely. We can safely build a submarine without having to understand the quark. We can accurately calculate the orbits of the planets without having to prove string theory. We can fully understand, predict, and manipulate our world right now, right here, at our scale.
That is a deeply comforting thought to wrap up on. It makes the grand, overwhelming universe feel surprisingly accessible, even if it is infinitely deep. It squarely puts the power of understanding back in our hands, operating at our own effective human scale.
It really does. It elegantly reminds us that we are not scientifically insignificant just because we aren't made of the most fundamental stuff. We are the masters of our own effective reality.
Well, this has been an absolutely incredible journey through the hidden layers of reality, from the simple blue sky above us, all the way to the tearing edge of black holes, and right back down to the wooden table sitting in front of us.
It is always a deep pleasure to unpack these incredibly complex concepts with you.
Before we wrap up, thank you to all our partners, sponsors, and scholars who made this podcast and the research possible. We're truly grateful for your support.
And to our listeners, thank you for being part of this journey with us. We hope you enjoyed today's discussion. If you did, be sure to subscribe and support us in Patreon. And of course, you can write to us in comments if a specific topic needed to be covered, which help us all to grow.
Until next time, stay curious, keep learning, and let the search for wisdom guide you forward. Have a great day.